Hey everyone, this video is to help introduce our new unit, Unit 10, and the big goal for this video is to be able to understand the difference between polar and nonpolar bonds, which we looked at in the last unit, and polar and nonpolar molecules, which are something entirely different. Okay, so let's dive right in. I'm going to jump around a little bit through the slides because some of this stuff is for the overall unit. So this is our unit goals. I'm going to go right through to our next part. Okay, intermolecular forces, something we want to be aware of. This is going to be the crux of the whole unit. An intermolecular force is defined as the attractive forces between molecules. So it's going to be how much one molecule, for example, one H2O molecule, attracts a second H2O molecule. So we haven't looked at this at all yet. We looked at bonds within a molecule. But this is about how one molecule attracts another. So that's an intermolecular force, or it's often just given the acronym IMF, is how we describe it. Now that's very different from intramolecular forces. Intramolecular forces are the bonds. We spent the whole last unit really focused on those intramolecular forces. But this is going to be doing both essentially in this unit. So the difference here, another way you can look at it, right? An international flight will fly from one nation to another nation. So kind of thinking of it that way. But okay, so big difference here. If we were to vaporize 1 mole of water, right, go from a liquid to a gas, that would take 41 kilojoules of energy to vaporize that. If we were to break all the OH bonds in 1 mole of water, that would take 930 kilojoules of energy. That would take a chemical reaction pretty much to do that. Much big difference. Pretty big difference. So essentially it's sort of like if you're swimming in the pool, if you literally chop the water, your hand is passing through and breaking apart, you're pretty much separating water molecules from each other. You're not actually breaking off hydrogens and oxygens, like that would be incredible. All that you're doing when you chop through the water is separating those molecules that are attracted to each other. So you're disrupting the intermolecular forces. It would require a chemical reaction to actually break OH bonds. So nothing you do naturally, even swimming in the water, is going to break OH bonds. Even swimming is breaking intermolecular forces, and that's much different than breaking the OH bonds themselves. So, general thing is intermolecular forces are much weaker than intramolecular forces. So in other words, it's much easier to pull apart 2 water molecules than it is to take a single water molecule and break bonds. That's a whole different thing. Breaking bonds is intramolecular. Separating water molecules is intermolecular. And don't worry, we'll spend a lot of time on this throughout this whole unit. So some examples of this of intermolecular forces that affect things are boiling point, melting point, heat of vaporization, heat of fusion. We'll learn about these later. Okay. This is going to be important in a moment in understanding really when we talk about whether a molecule is polar or not. So I might jump back to this in a second. Okay, as far as our general idea, how do we figure out how to predict whether a molecule is going to be polar or not? The whole molecule, not just bonds. First thing, draw the Lewis structure. Some of you guys have become amazing at that and very quick as well. Find the molecular geometry, right? Is it bent? Is it tetrahedral? Is it trigonal planar? All of those things. Draw in 3 dimensions, or at least have a 3-dimensional understanding of what you're looking at. Decide if the dipoles pull electrons equally in opposite directions. We're going to go more into that if you don't remember what a dipole is. And then, yeah, so let's go from there. Here's our electronegativity values, just as a reminder, right? Electronegativity is how much an atom attracts electrons in a bond. Okay. We're going to skip over this for now. I'm going to jump right into, okay. So you may recall in the last unit we looked at a polar covalent bond. And hopefully you remember that the idea was that what made it covalent, the bond, was that the electrons were shared between the atoms, right? There wasn't a big enough difference in electronegativity for one atom to actually steal an electron completely from the other. They still shared them. But what made it polar was that the electron spent a lot more time with one atom. It was staggered to one side of the bond, right? That's what generated and made it polar. And when that happened, we said that we were creating one side of the bond. It was a partially negative side, right? Here's our partial symbol. And the other side of the bond was a partially positive side where, for example, the electron that hydrogen used to have now was not spending nearly as much time on that side of the bond. So that was generating a charge, essentially, and we said that that was polar because we're creating almost like a north and south pole of a magnet. We're creating two different poles, and that's also called a dipole. So in a polar bond, we're creating a dipole. Di meaning two, poles like poles of a magnet. So we've got sort of a south end and a north end, essentially. What this is showing, essentially, is an electron distribution map. So it's almost like a heat map, where the red is where you see the most electron density. This is actually an electron density map. And the blue is where you see the least electron density. So we notice how the electrons are definitely staggered toward fluorine side, essentially. Now when we did our Lewis structures, they would look like this. And what's a new addition here that I really wanted to point out is that there is an arrow here parallel to the bond. And the idea with the arrow is you're supposed to make it parallel to the bond, and you point it toward the atom in the polar bond that has a higher electronegativity value. In other words, you're kind of showing with the arrow the flow of the electrons. So in this case, the electrons are flowing from hydrogen toward fluorine, essentially, just like we saw in our electron density map. Another sort of thing to help remember with this arrow is that the partially positive side, or the side with the lower electronegativity, the arrow gets a little plus on that tail, almost as if to say, like, this is the plus end, pretty much. Okay, so what I also showed here, notice how I have two of these. The reason why I showed two is I wanted to emphasize that because we created these dipoles, partially positive end and a partially negative end, this molecule, first of all, is now polar. So because we have our only bond present here is a polar bond, we said in a polar bond electrons are kind of distributed more to one side. The same thing is happening with a polar molecule. A polar molecule is defined as being polar if there's an asymmetrical electron distribution. In other words, if you look at the entire molecule and all of its bonds included, and if after you've looked at that you realize that the electrons are distributed to one side of the whole molecule, then it's going to be a polar molecule as well. So in the case of HF, it just so happens that the only bond is that one bond. So in the entire molecule, since the electrons are staggered, in this case to the fluoride side, to the fluorine side, that makes the molecule itself polar. Now why that matters is because if a second HF comes into contact, the partially positive on the one HF will actually be attracted to the partially negative of the other HF, and they're going to want to, they attract each other pretty much. And this is what we call an intermolecular force. We'll define them more specifically later, but this is the broad idea, is that one molecule attracts a second molecule because of what's happening with those electrons. So let's look at some other examples of molecules and really try to evaluate what kind they are. Water, right? Classic water. Notice how as well this water is drawn in its proper bent electron geometry. That's going to be hugely important for what we're about to do. But okay, so we're going to evaluate the bonds first. We've got 2.1, 2.1, and a 3.5. Those are the electronegativities for those atoms. And so then we deduce, okay, a bond between H and O is a polar bond. So I'm going to go ahead and put in my arrow that shows the electron flow. It's pointing toward the higher electronegativity. Notice how it's parallel to my bond. And the plus end is at the lower electronegativity. Okay, I'm going to put in my partial positive, my partial negative, partial positive. At this point, we should understand that those are created because of the flow of the electrons. The electrons are now more concentrated toward the O, making it partially negative. And they left the H's to some extent, making those partially positive from what they used to be. But okay, so right now we're looking at these two bonds and the general pull of the electrons, and we're trying to make a judgment of the whole molecule. We've evaluated both of these bonds and determined, yes, those bonds are polar, but we're trying to make a judgment about the entire molecule. That's the difference here, is this entire molecule actually polar? And we can kind of see what happens to the overall electron distribution. So if we look at our arrow over here that's up and to the right, this is sort of a physics concept, but we can think of that as being in vectors of up and to the right. And if we look at our dipole arrow over here, we can think of that as being up and to the left. Now you can probably realize that it probably makes some sense that this right arrow is directly canceling out this left arrow, right? So what's actually happening is the components of the electron pull are actually adding up, and it just happens to be literally adding upwards. But I mean adding up as in adding together. The dipoles are actually adding into the same direction, meaning that there actually is an asymmetrical electron distribution. In general, for the H2O molecule, the electrons are being pulled upward. So this is what we call the dipole moment for water is actually in the up direction in general, if we consider what happened with all the bonds. So the electrons, there's actually a general pull upwards. And if we look at our electron density map of water, we see that as well. The electrons are definitely being channeled toward the top. So that's going to create a broad general partial negative up here and partial positive down the other ends, essentially. So because of that, because we are generating a broad molecular dipole, this is a polar molecule. So water is classically, famously, a polar molecule. It's hugely important for what we're going to see for the rest of the unit, that water is a polar molecule. And a big part of it is because of that bent structure, which I'll talk about in a second. But yeah, the idea here is the dipoles added up in the same direction. The electrons are staggered to one side of the molecule, in this case more to the upward part. So that makes it a polar molecule. Okay, let's look at a counterexample though. CO2. So we evaluate each of the bonds again. We've got 2.5, 3.5, 3.5. Okay. If we do the electronegativity difference, we do find that each of these bonds are polar. So I'm going to go ahead and put in my partial negatives, partial positives, and my dipoles. Okay. Now what happens in this case actually, even though there's a pull to the left side toward the oxygen, there is an equal and opposite pull toward the right side, toward the other oxygen. In this case, we say that the dipoles are actually canceling each other out. And what happens in that case is that you actually end up having a nonpolar molecule. There are equal and opposite dipoles on here. In other words, there's a molecular symmetry of the electron distribution. When that happens, the molecule itself is not generating a general pull of electrons to one side of the molecule. They're kind of more symmetrically spread out, and so this molecule is actually nonpolar. Okay, so let's take a minute to talk about sort of the gravity of what all this means. If we look at water again for a moment, think about the state of matter that water is at room temperature, just regular room temperature where you are now. The reason why it's that liquid state is because one water molecule, being polar, attracts to a second water molecule which is also polar. To some extent, they stick to each other with the partial negatives of one attracting the partial negatives of the other. That's our intermolecular forces we're talking about. So that's part of the reason water is a liquid at room temperature, because they do attract each other. There is some sticking that's happening, called intermolecular forces. Now if we consider CO2, we just said CO2 is a nonpolar molecule. In other words, it's not generating a magnet of itself. It's not really generating so much of a sort of a stickiness. So think about what state of matter carbon dioxide is at room temperature. A gas, right? Because the one CO2 molecule doesn't attract very well a second CO2 molecule, so they flow freely as a gas. And that's a big part of the reason for it. So this is all why this is occurring, essentially, a big part of it. Okay, so at this point we've said if there's an asymmetrical electron distribution, like in water, or an HF, that's going to be a polar molecule. You have two poles to the molecule, essentially. If you have a symmetrical electron distribution, like with CO2, that's a nonpolar molecule. Those poles in either direction directly cancel each other out, and it makes a nonpolar molecule overall. Again, big difference between nonpolar molecule and nonpolar bond. Okay, because each of these bonds were actually polar, but the molecule itself ended up being nonpolar. let's take a moment to then look at what we just saw in terms of our electron shapes. So if we go back over here to our shapes, CO2 was linear, right? So it's safe to say that if you have a linear molecular geometry, in which case both of the bonding atoms are the same type of atom, same electronegativity, that's going to be nonpolar essentially, because you've got equal and opposite pull, right? Linear is symmetrical. If we look at trigonal planar, another one of our parent overall geometries, that is also going to have a symmetry to it. So if all of the atoms that are involved in the trigonal planar geometry are of the same electronegativity, or the same atom essentially, it is safe to assume that that trigonal planar geometry will be nonpolar, because there will be a symmetry there. Same thing with tetrahedra. There will be an equal and opposite pull in 4 directions, assuming that all four bonded atoms are the same atom pretty much. It is safe to assume then that's going to be nonpolar as well. It's when it becomes asymmetrical, like in a bent or a trigonal pyramidal, or a bent in this regard, like water was a bent like this one, right? Or if you really have atoms that are bonded in the parent shapes in this column that are significantly different from each other, that could also technically do it, right? There's always some nuance, there's always some exceptions, but this is the broad idea of this unit. Okay, so let me jump back down. And again, if we're looking at this HF, electrons are pulled to the right side in general, so that's a polar molecule. Ammonia, right? What's in Windex? Can you guess which direction these electrons are being pulled in? Hopefully you can see that there's 3 bonds here, but broadly speaking, there's an upward pull of the electron straight up, so that is a polar molecule. There's a partial negative technically up top, and a molecular partial positive down bottom. CO2 directly cancel out, right? It's linear, symmetrical, so nonpolar molecule. Carbon tetrachloride. This would be a tetrahedral technically, right? We've got 4 atoms bonded to the central atom. Also nonpolar. Even though each of these bonds are polar, in both of these molecules, every single bond is actually a polar bond. Entirely different from the fact that because of the molecule symmetry, the overall molecule is actually nonpolar because of it. O2. So essentially, if you have a only nonpolar bonds, it's almost always going to be a nonpolar molecule. That's another way to check. And then H2O, we saw, is going to be a polar molecule, right? There's a general pull in the up direction. So, diatomic molecules like HCl, for example, if the bond is polar, the molecule has to be polar, right? Because the bond makes up the whole molecule, just like we saw for HF. So here it is, for example, polar molecule. Electrons definitely gather to one side. Cl2, nonpolar molecule. All the bonds are nonpolar, so that helps us decide it as well. N2, right? These are both symmetrical as well, but there's not really much of an electron pull happening either. So if the bond is polar, molecule is also nonpolar, with some exception. So we have to look at the electron distribution of the entire molecule, start with individual bonds, then look at the direction of the polarity, if it's polar. In CH4, every bond is actually nonpolar, and therefore the molecule is nonpolar. In a nonpolar bond, remember, the electrons are shared pretty much equally. So if they're not even staggering to one side in a bond, they're not going to stagger to one side in an overall molecule either. CO2, symmetrical. The bonds are polar, but the molecule is nonpolar because of the symmetry. Ammonia, polar molecule, right? Molecules with polar bonds. Okay. A small thing we want to be aware of here is that for the cases, I mean, there's always exceptions in chemistry, right? For the case of our class, and it says not to get into too much specifics, but the lone pair electrons of central atoms influence electron distribution. For this class, consider molecules with lone pairs on the central atom to be polar, even though there are no polar bonds in the molecule. So that sort of makes sense, because if the way I sort of visualize it is, even if let's say I have 3 bonds on the central atom and I've got a lone pair on top. Even if all those bonds are nonpolar, That lone pair hanging out at the top is electrons in itself, essentially, so I just kind of think of that as being not symmetrical anyway. Here's a bunch of electron density maps. Again, emphasizing tetrahedral, all the same atom, nonpolar. In this case, though, notice how this is a tetrahedral technically. Actually, not just technically, it is a tetrahedral. But one of those atoms is not the same as the other four, so it actually is being pulled. The electrons are being pulled more toward the other chlorines than they are to the hydrogen. That makes a polar molecule. So that makes a big difference. This is not symmetrical, whereas this molecule is symmetrical. So there's actually an electron pull being generated on this right molecule, whereas they're spread relatively equally and symmetrically on this nonpolar molecule. Okay, and then here's the last part. We look at H2O again. Which of the following molecules have a dipole moment? So, in other words, an overall dipole for the molecule. Water. Here you go. Dipole moment, polar molecule for water. CO2. There is no dipole moment, right? The bond dipoles are canceling, but so because they're canceling, there's no dipole moment for the overall molecule, nonpolar molecule. SO2, if we evaluate the bonds, overall there's a downward pull, so that there is a dipole moment on the molecule, polar molecule. And then for CH, I'm actually not even I didn't even put the dipoles in because each of the bonds are nonpolar, so I consider this to be a nonpolar molecule. Okay, so that's it for polar molecules versus nonpolar molecules, and definitely contrasting them with polar bonds versus nonpolar bonds. To briefly summarize one more time, if all the bonds are nonpolar, the molecule will not be polar, right? Because the electrons are shared relatively equally, unless there's a lone pair on the central atom. So that's point number one. Point number two, if there's a polar bond and an asymmetrical electron distribution for the molecule, it only takes at least one polar bond to do that, then that means the molecule itself will be polar. Just try to visualize, are the electrons being pulled in one broad direction in the molecule? Last point, point number three. If there are polar bonds, but they are in equal and opposite directions because the molecule is symmetrical, that means the molecule itself is nonpolar despite having polar bonds. Thanks for watching, and I'm happy to see you guys soon to help out with this.